Hi students, so today we are going to see about geomagnetism. So geomagnetism is nothing but the magnetism related to earth. Suppose if we suspend a magnet, it will align in north-south direction. If we suspend a magnet normally, it will align in north-south direction. So from this it is obvious that there is some magnetic field associated with the earth, otherwise it will not align in that particular direction. Okay, so regarding this, okay, there were lot of thoughts, some theorem came. Okay, finally the most acceptable solution, or we can say the best possible solution for the reason of Earth's magnetism is what is conveyed. Even that also, for the time being, till now, that is the possible explanation which is given. But again, then, okay, it is not very sure that is the reason, but based on certain evidences and points, that is how the information we have. Okay, I'll explain one by one. Okay, initially Earth has got a small amount of magnetic field associated with it. Okay, somewhere around like 0.1 to 0.5 Gauss. Okay, this kind of small magnetic effect is there with Earth. Okay, or approximately we can say this is somewhere around 10 raised to minus 5 Tesla, we can say, in SI unit. This much magnetic field we can see around Earth. Okay, so initially it was thought that, okay, initially the first theorem which came in this regard is like there is a big magnet inside Earth. Okay, it was considered like there is a big magnet inside Earth. Okay, this was the first assumption. Okay, there is a big magnet inside the Earth. Okay, so this is the first assumption under this point, but this was rejected later easily. Why? Because when we found that the temperature inside Earth is of Curie's temperature, means very high level temperature, very high temperature is there inside Earth. So if we keep a magnet at such high temperature, it will not work. Magnetic properties will be vanished at such high temperature. So Earth's inner area has got very high temperature, so this will not work there. Okay, so that is why this theorem was rejected. Okay, there is high temperature inside Earth. Okay, inside Earth. Okay, or this level of temperature is called Curie's temperature, Curie temperature. Okay, Curie temperature. Okay, and at such high temperature, magnetic properties will vanish. Okay, so this theorem is what rejected. Okay, the main reason is because Earth's interior area, interior surface or interior area has very high temperature and their magnetic properties will not work. Okay, so this was the first theorem. This is rejected. Is it clear? Okay, so again after that second theorem came. Okay, what is the second theorem? Theorem 2. This is called the dynamo effect. Dynamo effect. So this is considered as the best possible explanation in this regard. Okay, certain things we may not be able to say exactly that it is a fact in scientific terms. We cannot say this is the fact, we cannot say. Okay, so that will continue as a theorem. Okay, they will continue like a theorem and we will consider that as the best possible explanation until now. That's it. It may change. Okay, so likewise theorem 2, dynamo effect, which is nothing but inside earth there is molten metal. We know inside earth it is high temperature, and at high temperature there is molten metal like in nickel, iron and all. And since earth is rotating, because of this high temperature all the free electrons will come out. All the free electrons will come out from its atoms, and at a high temperature, okay, they will come out, and these atoms will be ionized. This molten metal atoms will be ionized, and when earth is spinning, when earth is rotating, what will happen? Obviously these ionized atom also will be rotating. That will create current. If there is current in this direction or this direction, there will be magnetic field. This we have seen. Okay, moving charges and its effects. Okay, magnetic effects of electric current we have seen. So same thing is happening here. So that is the called dynamo effect. Okay, so there is molten metal, okay, just like nickel, iron, okay, inside earth, okay, at a high temperature, okay. So molten metal at a high temperature. This molten metal will get ionized, at this high temperature, when free electrons leave the atom. Okay, so at this high temperature electrons will leave the atom and this molten metal will get ionized. Okay, means that atoms will get ionized. So ionized atoms will get its rotational or circular motion, will get its circular motion when earth rotates and constitutes current. This will create magnetic field. Clear? Please note it down. This is the reason which is considered as the best possible explanation for the magnetic field presence in Earth. Is it clear? Okay, note it down. Okay, so this theorem, how it works? Okay, suppose Earth is there, and Earth will be what? Will have its rotation, okay. So when Earth is rotating, okay, suppose ionized atoms are there, okay, if they are rotating like this, okay, ionized atoms, when they are rotating like this, okay, when they are rotating like this, it will constitute current. So if the current is moving in this direction, there will be magnetic field. Okay, if the current is, see here, this is moving in this direction, there will be magnetic field in the downward direction. Correct or what? So we can say what? Magnetic field in this direction. Correct or what? If there is current in this direction, there will be magnetic field in this direction. So because of this movement of ions, because of movement of this positive charges, there is current and there is magnetic field. This is called the dynamo effect. This is considered as the reason for Earth's magnetism. Clear? So there are some additional arguments. With support, which supports this theorem. Okay, one example is number 1, moon. No molten fluids. Moon, there is no molten fluids. So molten fluids is considered as the reason for magnetism, but in moon there is no molten fluids, and we can observe that no magnetic field around moon. No molten fluids in moon, and there is no magnetic field also. This point is supporting this theorem. Okay. Number 2, Venus rotation is slow. Venus. Molten fluid is present. In Venus, molten fluid is present, but rotation is low. So we know that I is equal to what? dq by dt or q by t. So when this dt factor, when this increases, current decreases, naturally magnetic field decreases. And since Venus, the rotation is slow, magnetic field is less. We have observed this also. So this point is also supporting this theorem, dynamo effect theorem. Third example is like Jupiter. Jupiter rotation is fast. So I is more here and more magnetic field. So in Jupiter, molten metal is present. Molten fluid is present. I could say here metal. Fluid only, but metal. This is present, but here this rotates very fast. So current is also more. Okay, so magnetic field is more in the case of Jupiter. This is also observed. So magnetic field is more in Jupiter. The reason when we think this is matching with this theorem. Okay, that is what this is considered as the reason for Earth's magnetism, dynamo effect, molten fluid, its rotation, effect of current, and resultant magnetic field. Okay, please note it down. Okay, clear? Okay, we have seen the reason for the Earth's magnetism. Now we will study in detail about it. Suppose if we consider Earth, okay, this can be considered as the axis of rotation. This is, I am writing this as geographic north and geographic south. Geographic north and geographic south. Why I am writing geographic north and geographic south? Because soon we will have magnetic north and magnetic south and all. Okay, so this is axis and this is actually what? The equator. Okay, equator. Okay, equator. Now when we consider the magnetic field of Earth, we can observe that it seems like a magnet is kept, a big magnet, if we keep like this. Suppose if this is north pole and if this is south pole, how it will behave? From the north pole, the magnetic field lines will emerge. And it will join at the south pole. Correct or what? This is how it will behave. So same thing we can observe in the case of what? In the case of Earth. This is what we are able to observe. That is, okay, so yes, so it is just like from the geographic south, near to geographic south, a little bit away, magnetic, just when we keep the magnetic needle, this is how the field lines we are able to observe. Okay, so this is how we are getting. That is, the north pole, the real north pole of Earth magnet. Suppose if we consider magnet inside Earth, the real north pole is where? Near to the geographic south. The north pole of magnet is near geographic south. But the name they have put in such a way that, please understand, this is considered as magnetic north. This is considered as magnetic north, and this point is considered as magnetic south. So the names are in such a way that geographic north, magnetic north, geographic south, magnetic south. But behavior wise, this behaves in such a way that magnetic south will have the north pole of the magnet. Is it clear? Okay, so just like EMF is what? EMF is the work done per unit charge. EMF is actually the work done per unit charge to bring the charge throughout the circuit in a closed circuit. EMF, electromotive force, but it is not force. So same way we can say the name given is what? Magnetic north, but this is south actually. Okay, behavior wise south. We should understand this difference. We'll giving some name like Tirunyanam or Jnanamani, something like that. But the person, when he grew up, he is not learning anything. So he doesn't have, Jnanam means knowledge. Jnanam in Tamil, the English term is knowledge. But he doesn't have, the name is given like he is something related to knowledge, but he doesn't have any link with the knowledge. Same way, name will be given, the behavior may be different sometimes, right? Same way, this is, I am insisting again and again, no more confusion should happen. This is geographic north, this is magnetic north. This is geographic south, this is magnetic south. This is what is the names. But the behavior wise, magnetic field lines will emerge from here. Magnetic field lines will emerge from where? near to the south or at magnetic south, and it will go to the magnetic north. When we consider a general magnet, what will happen? If this is south and this is north, from here the magnetic field lines will emerge. Magnetic field lines will emerge, correct or what? It will join at the south. Clear? This is what is happening here. Please note it down. Okay, so suppose if I draw a line like this, if I draw a line like this, okay, this angle is actually 11.3 degree. Okay, even Earth's rotational axis is also slightly tilt from the vertical. Earth's rotational axis is also slight tilt from the vertical. So even with that rotational axis, okay, so we can say this is magnetic axis, and this is what? Rotational axis. So the angle between rotational axis and magnetic axis is 11.3 degree, and this changes. This changes means in 1000 years. Okay, taking it, the change will be very slow. Okay, a small change will happen in 1000 years and all. Okay, but for the time being, currently this is considered as 11.3 degree. This is how. Okay, now this is equator. Okay, this is what? Geographic equator. Now we are putting here geographic equator. Now same way we can draw what? If this is the magnetic axis, I can draw like this. Okay, so this is what? Magnetic equator. Okay, so this is magnetic equator. Clear? Magnetic equator, geographic equator. Rotational axis, magnetic axis. Okay, the angle between them 11.3. Geographic south, magnetic south. Geographic north, magnetic north. But this is actually, if we consider a magnet, this is north pole, this is south pole. Clear or what? Now there is something called a dip circle. Dip circle is a needle which can be kept in vertical plane, not like this, vertical plane. So if we keep a dip circle, it will show the line of field, that is magnetic field lines it will show. So if we keep a dip circle at the south pole, this will show vertical direction. Suppose if we keep dip circle, okay, dip circle is like a vertical, okay, okay, this will show what? Okay, this will show the magnetic field lines, okay, magnetic field line direction. So this will show vertical direction if we keep at magnetic south. Okay, so this is the direction of, this will be the direction of what? Field lines. And if we keep here the dip circle, if we keep here, this will show again vertical towards the earth. This will show towards the earth, away from earth. So this also, this will show vertical, and here also this will show vertical. Dip circle will show vertical at poles. Dip circle shows vertical or dip circle point vertically, dip circle points vertically at magnetic poles. Okay, vertically. Okay, so suppose if we are standing here, and if we keep the dip circle, it will be showing vertical direction, and if we stand here and if we keep the dip circle, it will show the vertical direction downwards. Okay, and so this is one important point. Okay, remember this. Okay. Okay, clear. Now at magnetic equator, not geographic equator, at a magnetic equator, suppose if we consider this magnetic equator, so here at a magnetic equator, dip circle will show what? Horizontal. It will point horizontally. Okay, dip circle points in horizontal direction. So dip circle points in horizontal direction at what? At a magnetic equator. Okay, okay, collect these informations please. Okay, clear? Okay, fine. Okay, now regarding dip circle, okay, this dip circle will give us proper idea about the direction, and from that we will be able to measure the magnetism or magnetic field of Earth. Okay, so one term which we should study is nothing but angle of dip. Angle of dip. Okay, angle of dip, or we also name it as inclination, angle of inclination. Okay, or angle of inclination. Okay, this is just like when we use a dip circle is a needle, or okay, just like a compass. Okay, a needle which is kept in vertical plane, and when we keep at a point, okay, if we keep it at a point, it will show us what? It will show us the direction of Earth's magnetic field. Okay, now where we will keep this dip circle? Okay, sorry, what? Yeah, dip circle. Okay, where we will keep this? We will say that we should keep the dip circle in magnetic meridian. Okay, so what is magnetic meridian? Magnetic meridian is, I will suppose if this is Earth and if this is magnetic north and this is magnetic south. Suppose if we consider a dip circles at some place, okay, it should be in the magnetic meridian. We are saying, what is magnetic meridian? Magnetic meridian is like if we consider a point, okay, this is the globe, this is the globe, earth. Suppose if we consider a point, if we cut this point along a plane which includes this point magnetic north and magnetic south, we will be getting a plane. That is what is magnetic meridian. Okay, what is magnetic meridian? Okay, magnetic meridian is nothing but, if we consider a point, if we consider a point on Earth's surface, okay, if we consider a point on Earth's surface, if we cut a plane including the point magnetic north and magnetic south, that plane is what? Magnetic meridian. Magnetic meridian. Okay, suppose three-dimensionally we should imagine. Okay, suppose if this is a globe, okay, this is a globe, I consider a point here. Now what I do, I considered the magnetic north here, magnetic south here. If I cut like this, I will be getting a plane. That is what is magnetic meridian. Suppose this is globe, I consider a point this side, or I consider a point here. So I take this point, magnetic south, magnetic north. If I cut like this, I will be getting a plane. That is what is magnetic meridian. Okay, hope you understood. Okay, so we should understand three-dimensionally. Okay, once again I'll explain. This is a globe. Okay, this is a globe, and in the globe, okay, you can just imagine, if this is a point, I will consider this point magnetic north, magnetic south. Then putting these 3 points together, if I cut, I will be getting a plane. That is what is magnetic meridian. Okay, dip circle always we should keep at magnetic meridian. I mean, dip circle we should align with the magnetic meridian. Suppose if this is the point, okay, here there is a point. So I will try to draw this. We will try to draw. Okay, you have copied this. Okay. Suppose this is Earth. Okay, so this is magnetic north and this is magnetic south. So suppose if I consider a point here, okay, this is three-dimensional, so I should consider like this. Okay, so if I consider a point like this, then how I should cut? I should cut if this is the point, and then this point, this point, this point, I should cut considering these 3 points together. So I'll be getting a plane like this, a plane like this. So at this point I should keep the dip circle in this magnetic meridian plane. I should not change the plane like this. So if I do like this, okay, if I do like this, okay, see, so if I am trying to cut a point with this, then what? I am getting a plane like this. Suppose if the point is here, if the point is here, okay, I am cutting around, keeping this point magnetic north and magnetic south. So the plane will be like this. Okay, suppose if this is earth, this is earth, if here the point is, then this is how the plane is. Correct or what? Okay, so this is how the plane is. Now I should keep the dip circle in this plane. I should keep the dip circle in this plane. Suppose if this is a dip circle, then I should keep the dip circle in this plane. Okay, so this is the plane of dip circle. I should not change the plane of dip circle. I should not change the plane of dip circle. That is what I am telling. The dip circle should be kept in magnetic meridian itself, and we will make the measurements. Okay, so you have got the idea about what is magnetic meridian. If we consider a point, that point magnetic north, magnetic south, cut. If you take a watermelon, take a point, consider magnetic south, magnetic north, cut. That is what is magnetic meridian. Then you can have your watermelon. Okay, if you want to see, you can see like that. Clear or what? Anything. Okay, any but three-dimensional or any what globe you can take, and you can try this. Any sphere, I mean any sphere you can take, you can point and tick. So this is magnetic meridian. And remember the dip circle, if the dip circle is vertical, okay, needle is there. So this dip circle I should keep in magnetic meridian. If this is the magnetic meridian, I should keep like this. I should not tilt. Okay, clear. So what is angle of inclination? In order to tell the angle of inclination only, I said magnetic meridian. Why I am saying about magnetic meridian? Because dip circle we should keep in magnetic meridian and to measure. Now suppose if we have kept the dip circle in magnetic meridian, okay, magnetic meridian, then what is the angle of inclination? Angle of inclination or angle of dip. Okay, angle of inclination or angle of dip. Angle of dip, both are same. Okay, so angle of dip is the angle in which Earth's magnetic field makes with its horizontal. Okay, so makes its horizontal, or we can say generally with the horizontal direction. Okay, see, suppose if the dip circle is pointing like this, now this is the direction of what? Magnetic field of Earth. This is what is the direction of magnetic field of Earth, considering this as magnetic meridian. I am keeping the dip circle in magnetic meridian, looking at it is pointing in some particular direction. Now for me, what is this? This is what is horizontal. So this angle is what is the angle of dip. Obviously the horizontal component of Earth's magnetic field also will be in this direction, and vertical component of Earth's magnetic field also will be in this direction. Clear or what? So angle of dip is the angle in which Earth's magnetic field makes with the horizontal. Whether I take its with the horizontal is also fine. With its horizontal means that its magnetic horizontal component of magnetic field. That's it. Okay, this is what is angle of dip. Okay, so if this is the angle of Earth's magnetic field, okay, so with respect to the horizontal direction or horizontal component of magnetic field, what angle it makes, that is what is dip angle of dip or angle of inclination. considering this should be kept in magnetic meridian plane. Okay, means this plane should have magnetic north and magnetic south also. Okay, that is what the meaning is. Now, okay, please copy this. Shall I erase this? Okay, now what can we say? Now this is Earth's magnetic field. Earth's magnetic field is actually what? Horizontal component of magnetic field also, then vertical component of magnetic field together. Okay, these two are there. So we can say that the horizontal component of Earth's magnetic field, the horizontal component of Earth's magnetic field is what? BE cos dip, correct or what? Can we say like this? BH is equal to BE cos dip. Same way, vertical component of Earth's magnetic field, this is nothing but what? Earth's magnetic field into sine dip. And what is also clear? Earth's magnetic field is equal to what? Root of what? BV square plus BH square, correct or what? Okay, now another thing is like suppose if we take BV by BH, BV by BH is what? BV is BE sine dip divided by this is nothing but BE cos dip. So this and this can be cancelled off. We can say that tan of dip angle is equal to what? BV by BH. Remember all these relations. Remember all these relations. Tan dip is equal to BV by BH. Remember all these. Okay, please note it down. Okay, copied. Okay, now this dip angle will be different at different places. Okay, if we start exploring from magnetic south, okay, and moving all the way to magnetic north, in whichever direction, if you want we can go in this way, then this will be the magnetic meridian. If you want we can go in this way, then this will be the magnetic meridian. If you want we can go in this way, that time this will be the magnetic meridian. Wherever we are keeping the dip circle, okay, that dip circle, if it is in a plane, that plane should have magnetic south and magnetic north also. That is the condition, means it should be in the magnetic meridian plane. Now what will be the angle of dip? Okay, at this is magnetic south. Okay, okay, so this is magnetic south and this is magnetic north. So at a magnetic south, what direction the dip angle will be? Angle of dip will be in which direction? Okay, so if we keep like this, this is going to be the direction of dip needle, okay, or Earth's magnetic field at the south pole. So means if we consider the horizontal direction, the horizontal component of magnetic field will be 0 here. Horizontal component of magnetic field will be 0 here. Entire dip circle will be in the vertical direction. And here also the horizontal component of Earth's magnetic field will be 0 here. Clear or what? Okay, clear? So here the angle of dip will be what? 90 degree. Here also the angle of dip is going to be 90 degree. Clear? 90 degree means whether positive direction or negative direction, 90 degree I am saying. And what will be at magnetic equator? If we consider the magnetic equator at this point, what will be the direction of field lines? Field will be in horizontal direction. So here the dip needle will be in horizontal direction, and the vertical component of magnetic field will be 0. Entire Earth's magnetic field will be what? Horizontal component only. Same way here also. Clear? So the angle of dip will be 0 at equator. Which equator? Magnetic equator. Clear or what? Copy this. Okay students, so angle of dip is the direction of Earth's magnetic field. Okay, direction of Earth's magnetic field makes the angle of Earth's magnetic field makes with the horizontal direction or horizontal magnetic field. That is what is angle of dip. Okay, so what we need to consider when we look at Earth's magnetism, magnetic north, magnetic south. At magnetic south only actually the north pole of the bar magnet if we consider. Okay, Earth as a magnet. Okay, and at a magnetic equator the angle of dip will be 0. Magnetic poles, the angle of dip will be 90 degree, and the dip circle we should keep in magnetic meridian. Okay, we should have this in the mind. Okay, okay, hope you have copied. Next one, we should understand geographic meridian also. Geographic meridian. Okay, so what is geographic meridian? If we consider a point, cut a plane along that point, putting geographic north, geographic south and that point in the plane. Okay, that is what is geographic meridian. Okay, considering a point on Earth's surface, if we cut a plane, including geographic north, geographic south and the point, the plane we get is geographic meridian. Okay, so geographic meridian, suppose if we just like a magnetic meridian, if we consider Earth, if we consider a point, keep this point magnetic north, magnetic south, cut a plane. So that plane is what is geographic meridian. Is it clear? Please note it down. Okay, done. Okay, so suppose if we consider two planes, okay, if we consider two planes like this, if we consider two planes, okay, and this is another plane, this is another plane, and that plane can be shown like this. Okay, so if this is the point on Earth's surface, okay, if we consider a point on Earth's surface, this is the point on Earth's surface. Suppose if this is magnetic meridian, if this is magnetic meridian, which plane? This plane is magnetic meridian. This plane is magnetic meridian. Then this is going to be what? Magnetic north, and this is going to be magnetic south. Magnetic south. Okay, this is magnetic south and this is magnetic north. And suppose if I consider this plane as geographic meridian, can you see this one? Okay, just like I have kept like this. Okay, so this one is what is geographic meridian. Then if this is the point, if I cut that plane along geographic north, and this is geographic south, so you can see the difference between magnetic meridian and geographic meridian. Okay, now if I consider the angle between, geographic meridian and magnetic meridian, that angle is called the angle of declination. Angle of declination. Angle of declination. Okay, when in simple terms we can say angle of declination. Any term we can use, I have used here D, you can use anything. Angle of declination, the angle between magnetic meridian and geographic meridian. That's it. The angle between magnetic meridian and geographic meridian. Done? Understood? Okay. Okay, you can consider, you see, I have drawn the picture like this. Okay, if this is magnetic north and this is magnetic south, then this is going to be the magnetic meridian. If this is geographic south and this is geographic north, if you consider like that, this could be geographic meridian. Okay, so any point which includes all the 3 points will be the corresponding meridian or plane. So angle of dip is where, if this is magnetic meridian, my angle of dip is here. So this is Earth's magnetic field, and this angle is what? The angle of dip. So angle of declination is here. Angle of dip is in which plane? Angle of dip is in magnetic meridian. Magnetic meridian. Is it clear, all of you? Angle of dip is in magnetic meridian. So if this is the Earth's magnetic field, I could show this is the vertical component of magnetic field, and this is going to be the horizontal component of magnetic field. Horizontal component of magnetic field. Is it clear? Okay. Okay, copy this. You should have pakka clarity on these concepts. Okay, done. Okay, now what I am going to do here is, I have drawn, this is a point. Okay, I took the plane. So this is the point, this is magnetic north and this is magnetic south. Okay, now suppose if this is another plane, if this is geographic north and if this is geographic south. If this is not geographic north or south, if it is a random plane, that also can happen. Just I have taken the plane between magnetic meridian and geographic meridian. So this is geographic meridian and this is magnetic meridian. Okay, you hope you can understand. Okay, this dotted lines, dotted points, this plane is what is magnetic meridian. Okay, now yeah, this one is angle of declination, angle of declination. Now in magnetic meridian we will be keeping the dip circle, we will be keeping the dip circle and we will be measuring. So this is what is angle of dip, angle of dip. Okay. Okay, so this is clear, right? Same thing I have redrawn. Clear or what? So this is all about angle of dip, angle of inclination, angle of declination, everything. Okay, geographic meridian, magnetic meridian, everything. Clear?